Hi, everybody. This is going to be a two-part lesson about the properties of light. We will break it into two parts based on the wave model and the particle model for light. And you'll be responsible for a little bit of vocabulary along the way and also being able to solve math problems. So at this point, if you do not have a calculator handy, you should get one. Make sure it's a scientific calculator. You definitely need to be able to handle very large and very small numbers when you're doing these calculations. Now, another handy thing would be to have the notes open so that you can take the notes as you go through this screencast. You can either type them in the document or you can write them in your notebook, but you definitely need some notes. Like, for example, you're going to have to know what's the wavelength and what's the frequency of a wave when we refer to those. What are their symbols? What units are they in? You'll need to be able to identify the speed of light and know the value for the speed of light. So, that you have to know. You need to know the equation to be able to calculate the wavelength or the frequency using the speed of light. You will need to know the forms of energy on the electromagnetic spectrum. And that is what we're going to cover in part one. What's wavelength, what's frequency, how to calculate them, and then how to identify what are the forms of energy on the spectrum. These other things with the frequency and Planck's constant and calculating energy in the atomic emission spectrum, those will be covered on part two, which will be another video and some different practice in the near future. So for this particular lesson, this lesson is about what's referred to often as the wave model of light. And in the wave model of light, okay, we view light as energy that is traveling in a wave. And it is, and there's lots of evidence for that. Waves can be bent or diffracted, and we've all seen light passing through like a prism or a gem, through a raindrop. We've seen them passing maybe through a diffraction grating. And waves can bend, and that's why we get the rainbow when white light passes through the prism and the different wavelengths bend at different angles, and we'll kind of know that by the end of this. So that's some evidence that, yeah, light does travel in waves. And every form of energy that travels in waves has something called a wavelength, which is the distance between two crests of a wave. So if you take the crest and the next crest over, the distance in between there, that is called the wavelength. Now, light waves are really, really small. So the distances are often going to be given in nanometers. And that's one of the reasons we had that in our metric conversions from Unit 1. We will definitely be converting our nanometers into meters, and I will review that with you in a little bit. So the frequency is how many waves pass a given point per second. Like if you're standing still and the light wave is traveling by, how many of those waves, being from crest to crest, will pass by the given point per second, okay? Now, per second is the unit. So a way to write that is second negative 1. Other times, students will write that 1 over seconds. I've also seen students write that like backslash seconds for per seconds. But all of these, there is a unit that means per second. And so instead of using all of these, what you're going to find is that we use that unit that is known as a hertz, not the rental car, but spelled the same way. The abbreviation for it is HZ, And it basically, it means, okay, per second. So for example, if we say that the frequency is 3000 hertz, that means there are 3000 waves passing per second. Now, I'm not sure if you've seen this before, this HZ, but if you look on like an old radio dial, you will see that the the numbers on the radio dial, let's say, for example, a popular radio station in this area is 96.9. That is actually 96.9 megahertz. I don't know if you remember mega from the metric that we did earlier, but that means that there's 96.9 million waves passing per second in that radio station's signal, because radio waves do move at the speed of light. So we'll get into that a little bit, doing some calculations, but the unit for frequency is hertz. One more thing I want to mention here, going back, did you see this symbol for it? That symbol, okay, that is the symbol font. And basically it's the Greek letters. And so this is actually a lower case l. So if you type a lowercase l, you highlight it, and then you convert it into symbol font, you would get this, lambda, which is the symbol for wavelength. And with frequency, okay, this symbol is another Greek letter. This one is nu, also the symbol font, and it's the Greek lowercase letter for n. So if you type a lowercase n and then highlight it and put it in the symbol font, you will get this, which is the symbol nu that we use for frequency. So amplitude is a wave's height from origin to crest. And so, for example, if this is our wavelength, okay, then the right through the center is called the origin. And so the height from the origin to the top, that is the amplitude. Okay, now the amplitude isn't going to come into play for us in any of the calculations that we are doing. Because what we are going to be doing is using the speed of light and the wave model for light to calculate either the wavelength or the frequency of the light. Okay. Now, one thing you need to know is that the speed of light right here, 3 times 10 to the 8th meters per second, that's a constant. Now, I usually get a lot of students who know the speed of light in miles per hour or some other units, but these are the units that I'm going to be using to do the calculations. And so this is definitely a number that you need to have handy in your notes, because we're going to use it to do a lot of calculations, okay? The wave model of light, remember, models can be mathematical. This is our mathematical equation, that the speed of light, which is c, is equal to the wavelength times the frequency. And here it is right here in words, okay? So you think about it, the wavelength is how many meters per wave, and the frequency is how many waves there are per second. And if you multiply those, then the wave cancels, and look what your answer is in meters per second. Well, that's the speed of light. So this equation, okay, works for all of the different forms of electromagnetic energy that are moving at the speed of light. As the wavelength gets bigger, the frequency has to get smaller to keep this as a constant. Well, that should kind of make sense, because if the waves are further apart, then less peaks will go by in a unit of time. And the opposite is true too. You're going to see then that as the waves get smaller, they're closer together, so they're more frequent, right? We'll see that as we look at the spectrum here in a little bit, okay? And then we're also going to use that equation to do some calculations today. So now this is the electromagnetic spectrum. And the electromagnetic spectrum is all the different forms of radiation that move at the speed of light, okay? You can see down here, we start with radio waves. Now, these are the forms that have the longest wavelength and thereby the lowest frequency because their waves are really far apart from each other. That means that in a given second, not as many of them will go past because they're spaced farther apart. They're peaks. And as the wavelengths get shorter, the frequency will get higher. So up here on the other end, we have our very shortest wavelengths, gamma rays, and they are so short, you can see in the 10 to the negative 13 meter range. So they are very, very short, which means that the frequency will be very high because the peaks will be very close together. And then what we're going to see tomorrow, or whenever we do part 2, is that the frequency is related to the energy carried by the wave. They're all moving at the same speed, but they don't all carry the same amount of energy. Like a radio wave is very low energy. Why? Because it's very low frequency. That's why a radio wave is safe to travel through the air. If one of them bumps into you, and I'm sure they are because there's radio waves all around us. How do I know that? Because if I got a radio out and turned it on, it could pick up a signal using an antenna. And so what happens here, and I just erase some of this here, sorry. But what happens here is, you know, if one of these waves bumps into us, it's not very big energy. It just bounces off of us. It can't penetrate our skin. It doesn't damage our eyes. As you move from this low energy up to this very high energy end of the wavelength, these waves become more dangerous. Like here, microwaves, they will cause water molecules to vibrate. And that's kind of like if you rub your hands together, you create a little heat. That's how a microwave works. Little water molecules vibrate and ta-da, they warm up. And next thing you know, your food is warmer. As you move up, you get into a lot of your cell phones are using waves to communicate that are, you know, in this area. Then you get to infrared. This is like waves that start to make your skin feel kind of warm. Like if you've ever had like a heat lamp or you go out in the sun, these are the waves given off by the sun that make you warm. Look at this tiny little section that we can see. Whenever we think of light, we think of what we can see. This is the little section that we can see, and we'll talk about that section separately. But you can see that the red end of that section, okay, has the longer wavelength. I don't know if you can see that. Just see how the red is here, and this is longer wavelengths over here. See that? And then the purple is on this end up here, and these are, you know, the shorter wavelengths. So even within that visible region, some of the waves are longer and some of them are shorter. And that's why when light passes through a prism, the longer ones bend further and the purple ones don't bend as far. And so the purple ones are always on the inside of the rainbow and the red ones are on the outside because they bend a little bit farther. But as you go up here, you can see these get a little more dangerous, like ultraviolet. And yes, the ultraviolet are near the purple end of the spectrum and the infrared are near the red end of the spectrum. But the ultraviolet, remember, they're given off by the sun, but they can damage your eyes. So that's why you need to wear UV protection in your sunglasses. And then these are the ones that burn your skin. So that's why you want to wear sunscreen with UVA and UVB absorbing compounds in there. Then you get to X-rays. Now, look, the energy is getting higher. You're going this way because the waves are shorter and they're a higher frequency. And now the energy is high enough, it can go through your skin, not quite get through your bones, but that allows us then to take pictures with X-rays. And they can go through like maybe suitcases, and that's how like airports will see what's inside of a suitcase by sending the X-rays through and then looking at the picture generated on the screen. And then you get up here to, on this end, the gamma rays, which are the shortest wavelength. They are the ones that are given off by radioactive elements when they undergo decay. And gamma rays are very high energy. They can damage your cells. Now, sometimes we use that, remember, in like a cancer treatment. They would use the fact that they're very high energy to damage cells and get those bad cells to die off and be swept away by the body. But then, if we are exposed to radioactive elements, they could kill off good cells too if we're not careful. So gamma rays can be very, very dangerous. But all of these forms of radiation move at the speed of light. So we can use the same equation to do calculations for all of them. We're going to use that in a minute. I can't get my slide won't advance. Oh man, that is not good. We got a little freeze up going here. There we go. Okay. So here's the list. Radio waves also include, radio waves also include radar waves. Okay. And then as you move down, okay, you're going from low energy to high energy. And notice that the high energy ones have high frequency, but they have very short, small wavelengths. We're going to do some calculations in a minute. And then there is the continuous or the visible spectrum. That contains all the wavelengths of the visible electromagnetic radiation. That's your Roy G. Biv that you've learned about in the past. The red end down here, that's your longer wavelengths, which means basically this is towards the lower energy side. And then as you go from red, orange on up through blue and the indigo violet, then this is where you get the higher energy because they have the shorter wavelengths, and that means they have higher frequency, higher energy. Okay. You and I, most of us, can see most of these. Occasionally, if someone's colorblind, they may not be able to see certain wavelengths. Okay. Some people can see a little bit more than others. Like, I know people, they can see red, but they're kind of cut off, out here at the edges where they maybe can't see some of the ones on the extreme. Okay. But that's called the continuous or the visible spectrum. Now, this is the equation then that we're going to use to solve problems with the wave model of light. So C right here, that stands for the speed of light, and that's in meters per second. Remember, it's 3.00 times 10 to the 8th meters per second. We're going to always put that in our equation for C. Wavelength, we want to put it in our equation in meters. So if we have it in a different unit, we're going to have to convert it into meters. Frequency, okay, we want to put it into our calculation as hertz, which is, remember, the same as per seconds. So we're going to use that equation to do some math problems, okay? And basically, what I would do if I'm you is you want to make sure you copy down some examples. As we're going through this, you do want to pause and, get your calculator. Make sure you know how to enter these on your calculator and you are getting these answers. Because I'm going to do 2 sample problems, And then we're going to have where you practice some on your own and just ask me for help. And that's why I made a screencast of this, is some people need to really go back and rewatch this or pause more. And then other people who are maybe just a little bit more, suited for algebra, and they remember how to do their math, their metric conversions, they might go through this a little bit faster. But we'll help each other, and you always have this examples to look back at if you put them in your notes. So it says here, green light has a wavelength of 492 nanometers. Okay, calculate the frequency of the green light. So the first thing is that our wavelength has to be in meters. So we have to take, and it's not writing for me. Not sure why it's locking up on me here. Okay, I saw spots there, so it must be working. All right, 492 nanometers. Okay, and we need to convert that into meters. Now you remember factor label from Unit 1. If you cannot remember, go back to Unit 1 and the metric notes. 1 nanometer is the same as 10 to the negative 9th, or 1 times 10 to the negative 9th meters. Now, why did I set it up like that? So that my nanometers would divide out, because nanometers divided by nanometers will divide out. And then my answer will be in meters. When you plug this in your calculator, remember that you have to plug in 1 and then use the EE and then enter the negative 9. Okay. Different people, their calculators were a little different. So yes, that could be a little different on some of them. Make sure you can use your calculator and you get this answer. Okay. Make sure you get this answer right here. Now, that's not the final answer. That's just the wavelength put into meters. What we're really trying to calculate in this is calculate the frequency. So we got to go back to our equation, C equals wavelength times frequency. And if we want to solve for the frequency, got to pull out our algebra skills. We can divide both sides by the wavelength, so it will divide out. And now we've got an equation that we can use. Frequency is equal to C over wavelength. We know C because it is always the same. It is a constant, 3.00 times 10 to the 8th meters per second. We know wavelength in meters because we just calculated it, 4.92 times 10 to the negative 7 meters. You can see now why we needed to have that in meters, so that the meters would divide out. And our answer, the label on it, will be per seconds, which is the same as hertz, which is indeed the unit for frequency. So you should plug into your calculator 3.00, then use that double E button, 8, and then divide by 4.92, use the double E, negative 7. Remember, some of you needed to put this bottom one in parentheses when you plug it in your calculator, some don't. Double check, try it in yours, and I got 6.10 times 10 to the 14 hertz. And you should round it to that. Like technically out here in the front, you get like 6.09. My calculator screen, let me see, 756. See, I'm rounding it to 3 sig figs because 3.00 has 3 sig figs and so does the 4.92. So that, since this next number was a 7, you have to round up 6.10 times 10 to the 14th hertz. Now I know the frequency of the green light. Let's try another problem. Local radio station broadcasts with a frequency of 97.3 megahertz. Okay. All of the FM stations, those numbers are in megahertz. I think the numbers that are on the AM, like 910 or, 1480, those are in kilohertz. And if you look inside of your microwave oven, they usually have a tag inside of there to tell you the frequency that your microwave oven is broadcasting at, in kilo or megahertz. And remember, those waves make the water molecules vibrate and wiggle, which causes them to warm up. But what is the wavelength? Okay, so first of all, the frequency has to be in hertz, not megahertz. So we're going to do a conversion. Let me get a good color that shows up well on here. Oh, we're stuck again. Okay, now it looks like we're good. Okay, so 97.3 megahertz. Now, I don't know if you remember, mega is million, mega millions, so 10 to the 6. But if you have to go look that up, please do that. A megahertz is the same as 1 times 10 to the 6 hertz, or a million hertz. So I multiply through, keeping my 3 sig figs, I got 9.73 times 10 to the 7 hertz. So there's the frequency of that radio station in hertz. So remember, we have the equation. C is equal to wavelength times frequency. That's a little tough to see, so I'll switch colors here in a second. But to get the wavelength, because that's what we're trying to find, what is the wavelength? You would have to divide both sides by the frequency. So C, okay, whoops, that's not actually what I wanted to do. Hold on. So wavelength is equal to C over the frequency. Again, C is 3.00 times 10 to the 8th, because that's the speed of light and it's a constant. The frequency we just figured out is 9.73 times 10 to the 7 hertz. And we plug those in to do our division. Now, the per second and the hertz cancel, because remember, hertz and per second are the same thing. But we plug this into our calculator, 3 times 10 to the 8th and 9.73 times 10 to the 7th. We divide, and I'm going to keep 3 sig figs again. I got 3.08, and I'm going to go back and use a different color. Sorry. A little tough to see. I was just trying to switch up colors, keep it fresh. But we get 3.08, and our unit is meters. So now we know the distance from peak to peak for the waves that are broadcast from that particular radio station. Okay. Now this concludes part 1 of the notes. When I pick up, I will review these 2 problems again, and then move on to the particle model of light and calculating the bundle of energy and how that ties into what we know about an atom. Okay? So, you got to do some problems using this equation, C equals wavelength times frequency. And if you have any questions about them, make sure that you see me. Good luck.